All right. Oh, I gotta turn the projector on. Can you all hear me on the coast? Yeah. Okay, great. All right. So I've had a few people ask me about the recording. I tried to record the lab last time we met on Thursday, but I guess it didn't work. So there's a few, like you have to press like 3 or 4 buttons. I think I'm getting better at that, so hopefully those labs will be recorded better in the future. I think they will. I'm testing it out here. I haven't typically recorded the lecture in this class like I have in my other class, but I am recording it this time. So it'll be a test and make sure that it gets done so that we'll have it on making sure that it works on Thursday. All right. I don't know why. There we go. Okay, the first thing I wanted to show today is the result that I got from doing. I forgot whether I did the exact same process or not, so the numbers might be a little bit off. I know I only asked you to chart the standard deviation here, but these were pretty sure those were the classes. If they're not, it'll be slightly different here. But you can see this is from our lab on Thursday. The result here of charting these statistics that show the difference in vegetation intensity over 5 different vegetation classes. So basically, as the elevation goes up, the difference in vegetation goes down. So it was actually Grant, Dr. Harley, that asked me to see if see what this analysis would produce, and I thought it was an interesting example of somebody actually asking a research question that could be done pretty easily. So you should get something like that. Your numbers may not be exactly the same. I even in class I mentioned that they're you may end up using the pre-processed elevation data where we didn't replace the values, or you may end up using that. In either case, you should see a similar pattern, which will be fine. Okay, so let's talk about what we're going to talk about today. Excuse me. And that's this cost distance modeling. Okay, so today's week 4. Is next week Mardi Gras? Or the week after? Okay, so it's 2 weeks after. So remember, in 2 weeks we won't have class, but not next week, I guess. That will be a class. So today we're going to talk about cost distance modeling.
Dr. Rager?
Yes.
Your PowerPoint is not showing up on our presentation or our screen.
Okay. Does it show up now?
Yeah.
I don't know if this was very interesting, but that probably didn't show up either. So this is the general way that your chart should look from the lab is what I was pointing out. Okay. All right. So yeah, cost distance modeling, and as a review, we've done this in previous labs. Talked a little bit about what's going on here. Straight line distance is basically the shortest actual path as the crow flies. Sometimes is the term that's used from each cell to a source And you'll notice that even when we're finding distance, that is something that requires a source. So we're finding distance from something. It's not just from, it's not universal. So we have the inputs to finding distance are always what you're finding the distance from, and in this case, it's just the grid that we want to use, and all of the grids have, to make a little more sense in a second, but all the values have an equally weighted cost associated with them. Okay, and that's because it's just a straight line distance. So every cell gets a value that represents the distance, straight line distance from that cell back to the original, what we call the source. So we call this the source, the location where we're finding the distance from. So here is here's that drawn into a simple diagram here. So if this is the source, the distance at that location would be 0, and the distance from the center of all of these cells is dependent on the straight line distance back to the source. So the value in those cells is dependent on the straight line distance. So if for example, the cell size was 1, the distance from the center of this cell to the center of this cell is, half the distance of a cell plus half the distance of the cell, which is 1 cell. Okay, the distance to this cell is 1, 2 cells. It's pretty straightforward, easy to think about. The distance down to this cell is 1, 2, 3 cells. Okay, so it's a pretty easy algorithm. It's just basically using the Pythagorean theorem. It's a little bit tricky, but not really that tricky when we start thinking about the diagonal distances. But this is just the square root of 2, because this would be 1, this would be 1. 1 squared is 2, so we get 2, and then you take the square root of that value in the Pythagorean theorem, and you get the square root of 2. So the distance from the center of this cell to the center of this cell, assuming the cell size was 1, would be the square root of 2. And so we could just multiply all of the values here, 1, 0, 1, 2, square root of 2, multiply those by the cell size, and we'd get the distances for any cell size. So if the cell size was 10, it'd be 10 times the square root of 2 from here to here, okay, and so on. So this really is very similar to a local operation where we're just applying a particular function. It happens to be the Pythagorean theorem to every cell in their grid based on a distance. So it's finding that distance back to the source. In cost distance modeling, we're going to think about it, and it really is an extension of finding straight line distance. So we can think about cost distance as being, we can think about straight line distance as being cost distance with only one factor considered, and that is the actual distance. ArcGIS calls it the Euclidean distance. All right, so the way that it's different is that costs are added to the equation. So we're gonna consider costs and not just distance. Okay. So the goal here is to produce a GIS layer depicting the minimum cost of reaching cells in a layer from one or more source cells. So it's the same inputs. Well, we have the same inputs, and we're going to add another one. So with cost distance modeling, we'll still have our source. So we still need to define the distance to where. Okay, it's the distance to a particular location. And so that source is, when we create a cost distance, the values in the cell represent the cost to travel back to that source. We can't create a cost distance grid and use it for any other purpose than to find the distance back to that source. So if we have another source that we need to start thinking about, we need to create a new cost surface. So those are the inputs: the friction, or the initial cost surface, and that friction or initial cost surface can be universal. Okay, so that's just going to be the cost to travel through a cell. We'll discuss that in a second here. Then you also need the source layer, just like you would for a regular fine distance. Okay, and then the output is going to be the cost distance. So far we've walked through this part. We need the cost or the friction data set. We need the sources, and we're going to get, as a result, we're going to use the cost distance algorithm, and we're going to get a gridded output of cost distance. Now, just like with Euclidean distance, there are some additional outputs. One of them is cost of direction. You can do cost allocation. There's a few other outputs. We're primarily concerned with the cost distance at this point. Then, let's say you want to actually find out how, not how far, but how to get from any point back to the source. Let's say the application of this is if we were planning to build a new road, or if we were planning to plan a route across a continuous field. Okay. So anytime, in GIS, oftentimes there's the problem of planning a route, right? And that route, if it exists on a network, it's often a better solution to use a vector analysis. If that route is across a continuous field, across a landscape, it's often better to choose a raster-based approach, and that's what we're discussing today. So finding a new road, a new railroad, which is the one we're going to highlight at the end of this, finding potential corridors for animals. If you understand, if you think you can model the behavior that an animal uses in deciding which path it's going to take, to minimize its cost to get from point A to point B, you could model areas where animals are more likely to go. In fact, you could, for example, modify your costs in a few different ways to find probable routes. Not necessarily the only route that they would take, but different routes. And so you could use that to plan for development or plan for conservation efforts. There are quite a few applications to this. So the first step is to do cost distance. Once you have cost distance, you can apply the cost path algorithm, and that provides a path. Okay, and this path, it actually produces a raster in most cases that represents the path, but you could convert that path into a vector, a line. Okay, so your friction surface is one of the primary inputs. The cell values of friction surface represent the cost per unit travel distance for crossing each cell. And so every cell gets a value, and the value in that cell represents the cost. It's a surrogate for the distance. And if you want to include distance as part of your processing, then you need to include that in the surface itself, okay, in the friction surface. So it assumes the cost for moving in any direction is constant. And the term for that is isotropic. And that sometimes can be an issue that people struggle with modeling using this technique or this model. In the vector world, it's easy to model traveling in different directions on the same path and having a different cost associated with that. In fact, it's necessary. Things like one-way streets. We could say, well, traveling from point A to point B, you can go 50 miles an hour. Traveling from point B to point A is impossible because it's a one-way street. Okay? Or if I wanted to go upstream in a river, the cost would be more expensive than traveling downstream in a river. Okay? Where it gets really tough is modeling something in a continuous field, like let's say with ocean currents is the example that I see most frequently. Okay, out in the ocean, it's definitely easier to navigate a boat or for a fish to navigate with the current than against the current. So if we're trying to model something like an oil spill or anything that's drifting with the currents, it would be difficult to do it in this using this modeling technique. Okay? Those are examples of anisotropic problems, and really the solution today is to often convert the continuous surface into a network, a very defined network of lines, so that we can assign different values to travel in different directions. So this won't do that, but there's plenty of problems that we can solve that do have that it's safe to assume the cost for moving in either direction is constant. Okay. So we can put barriers into a friction surface that represent locations that cannot be traversed. We can either code them as very high values if it's very unlikely that somebody would travel or something would travel through a particular cell, we can give it a very high value. Or if it's impossible, we can simply give it a value of no data, and that will work as a barrier, a way that would be impossible for it to be considered as a way to get from one point to another. Okay, we can have multiple cost factors. However, the algorithm expects you to provide it, to input into it exactly one friction surface or one cost surface. And so this can be accomplished through something that we've already discussed. Okay? So we're building on previous discussion here. We can take our input factors, for example, it might be slope, it might be land cost, etc., and we can add them together, add them up, addition of factors to produce a single friction surface. And in order to be able to add them, obviously the costs have to be on the same scale. So oftentimes it helps to conceptualize those costs into something that is applicable to the real world. Okay, so dollars or time or anything that represents cost or friction. Okay, so what goes on in terms of the internal workings of the process is that once the friction surface has been decided upon, the value for each cell is calculated one at a time while considering its 8 closest neighbors. And the cost to travel from any pair of cells is very similar to finding the real distance, except for what we're doing is taking the friction and adding those, because when we're looking at a pair of cells, we always have the friction in one cell, the friction in another cell, multiply that by the distance, and then divide that whole numerator by 2. Okay, so we're getting basically the average cost between those two cells and considering the distance. And then another algorithm is used to produce the cost surface grid representing the minimum cost of reaching the cells in a layer from one or more source cells. So this is where the source is considered. And along with minimum distance, the direction of the minimum distance path is calculated. And that is actually used as an input into the least cost path model. So and on this slide, I just thought we'd calculate this real quickly. If these numbers represent the costs, okay, to travel through these cells or the friction surface. Okay, the cost to travel from, let's say, this cell to this cell is 5 plus 2. Okay, then you multiply that by the distance. Let's just say the distance is 1, so it'll be easier. 5 plus 2 would be 7, and then you would divide that by 2. So the cost to travel from the center of this cell to the center of this cell would be, yeah, 3.5, exactly. And so we would have numbers associated with the cost to traveling between every pair of cells. The computer keeps that as the first step, although you never see the output of that. It has that value. Okay. Once it has those values, it can decide, which cells would be the least expensive path from the center of every cell. So it's a focal operation in a way at that point. Okay. And then we find the least cost path back to the source. So this would be the source. This is cost weighted. This is the direction. And the directions are coded as a number as well. And they're actually coded as these numbers right here. Okay. So everything has to be coded as a number. So when here in this cell, each of these numbers represents the cost, the total cost to get back to the center of this cell. So the cost to get from here to here is 5. The cost to get from here to here is 7.5. Okay. That's the accumulated cost to get back. So another way to look at straight line distance is it's the accumulated distance. This is the accumulated cost to get back to the center of the source cell. Okay. Here, now we could find out the path that it would take because at the center of this cell, instead of being coded as south, this would be southwest, 4 would be southwest. So what we're saying is the path to get back starts by going southwest. Then at this point, the path to get to this cell is 3, which is south. So that, if we were to ask the computer at this point, what is the least cost path back to the center cell, it would be going like this, like 4 to 3 to 1. And if we were to take the center of each cell, we could turn those into vertices, and we'd have a vector, this point, and this point that represented the least cost path. And this is a very small example. We're just looking at it's 9 cells here, but this is the process that goes on. Okay. Okay. So we followed that through. The cost or friction. The source is the other input. We get the cost distance algorithm. The main output is cost distance, but cost direction is also important. And in fact, the cost direction is cost direction is one of the inputs to the least cost path algorithm. Another one of the inputs to the least cost path algorithm is the destination or destinations. Okay, you can only have a single source, but you can have multiple destinations. And so you might be considering multiple locations, and so you could find out the least cost path. And then you could find out the total cost to each of those values. Okay, to each of those destinations. In fact, all that would be, so let's say we had a destination and it was a point. Okay, how do we find out what the cost is to travel back to the source algorithm if we have this cost distance grid? That's just a simple process of overlaying, like let's say that the point. Whatever the value is where that point touches the cost, sorry, it would be this grid. Whatever the value is where it touches the cost distance grid, which was 10.5, that's the cost that it would take to get back. All right. So here's an example using this this yellow point right here as the source. Okay. The first step is to create a cost distance grid, which is this, and the cost distance grid is based on a friction surface that's actually not included in this diagram, but that would be the cost distance grid. This is the cost direction grid right here. And this is actually the way it looks most of the time and when it's output into ArcGIS. ArcGIS automatically symbolizes it like this using these colors. But those colors don't really matter as much as what the values inside of them are. They're either 1, 2, 3, 4, 5, 6, 7, or 8, depending on whether the least cost path travels in north through the cell and so on. Actually, 1 is this way. So 1, 2, 3, 4, 5, 6, 7, 8. So traveling north to the south would be 7, I guess. Make sure I'm right. Yep, 7. Okay. In order, just as we have in previous lectures, we're going to follow through an example here and discuss how it works, and then I'll also download some data and do a demo in class here. Okay, so this is a project that we actually did 10, 11 years ago, but this analysis is still done a lot. When I was a graduate student at the University of South Carolina, and I've always thought that this was a pretty neat application for the least cost path modeling. And what happened is that Norfolk and Southern, they wanted to build a Firestone plant wanted to build a track so that their factory could be served by Norfolk and Southern. So we looked at the possibility of using GIS technology because at the time it wasn't as common to do that. So they'd send out surveyors out, and they would scour the landscape and try to find the best way to get this new lead track developed. So basically, this was a spur off to an industrial site. Okay, it's a costly process, and this. Our idea was not necessarily to totally replace the human element, but to at least narrow down the potential site that the potential path that they could go in and survey an exact path later. Okay, so the traditional method was using engineers, visual inspection of local maps using paper USGS quadrangles, and finding the path that way. And second, our method at the University of South Carolina, that was the name of the research center that we had there, was to acquire some LiDAR data, which was not very common at the time, but is now a fairly common method for creating elevation data sets, and use this information along with some ancillary GIS data to come up with a potential track location. And so what we had to do was to first decide on what the cost factors would be. And so we had to talk with the people that were experts in building tracks, and we found out that one of the biggest costs is preparing the grade. Okay, trains can't go anywhere near. Obviously, we know this, but they can't go anywhere near the same slopes that cars can go. Okay, they have a set grade that they can do. So there has to be some cutting and some filling to make a rail bed that doesn't go up really big hills or down really big hills. Okay. And then it actually costs quite a bit to build a railroad crossing. It's in the hundreds of thousands of dollars to install a rail crossing at a road. So every time a rail line is going to cross a road, there's going to be a higher cost associated with that. Sorry, was there a question?
Yeah.
Okay, and then stream crossings is also cost money because you have to build a bridge and trestle system to cross a stream. And then finally, just this is kind of like the raw distance cost. Finally, just building track costs money. So you want to minimize the length. I mean, obviously, you might be able to find a very, very cost-effective path if you traveled only on, and you never went up or down any hills, but you went way around a mountain. Well, would it be less expensive? At what point is it less expensive to just build a trestle or build a bridge partway through the mountain? So you have to assign a cost just to the track in order for it not to choose a very, very long path. Okay. All right. And so here is a diagram that's very similar to the ones that we would create in this class that could be executed in our GIS. Although this one's made more for showing as a figure rather than putting in Model Builder. But this is similar. So we have the original LiDAR data. We do interpolation to turn that into a digital elevation model. After we had the digital elevation model, there was each side, one of these circles. Traditionally, when we're doing Model Builder, is one operation. Well, each one of these circles is actually 4 or 5 operations. So finding out what area would have to be cut versus what area would have to be filled in order to produce a flat roadbed took a few steps. And then you calculate how much cut material, fill material would be needed for every grid cell. And then also we have transportation. This was a pretty easy process. So each road was just assigned, was turned into a raster grid, and then the value was assigned there was just a cost associated with traveling that. So anywhere outside of a grid that did cross the road had a value of 0. If it crossed a road, it had the value to cross that road. Okay? So if it was 100,000, the grid cells that crossed roads had a value of 100,000. All the other grids had values of 0. That's a road crossing model. That's a simplification of it, but it was pretty simple. Same with hydrography. These were assigned a value to build a bridge across. So we had a stream crossing cost. The rail cost itself, that was pretty much a constant. So this could be conceptualized as just adding whatever it costs to build a rail through that line. Could be $100. I don't know how much it costs to build rail through each section. And then you simply add these costs up and you feed that cost surface into a least cost path model using the rail line as the source. Okay. All right, so here is a visualization of the inputs. So this is the LiDAR data set that was used. Well, this is the DEM built from the LiDAR data set that was used to build the model. Okay, so that was converted as one of the inputs, as one of the primary inputs to the total cost. So this data set here is this guy right here, this total cost. You can see the effect of each cost in the model. For example, you can see these spikes. They don't show up very well, but they are, in fact, these are the individual grid cells. Okay, so it's not like the values go up and down. It's just the individual. This is a wall representing the cost across this road. Same with this road here. Okay. And you could see in these areas, these are high cost areas. They also happen to be low or high elevation areas. So it costs more to build a track over them because so much cut would have to be done to build a track over the top of these areas. Okay. All right, same with the low areas. Okay, those would be more fill areas. All right. Here it is as a two-dimensional. So this is the route derived from the traditional methods. So from the existing railroad to the Firestone, the new Firestone plant, which is right here. This is the way that was surveyed traditionally. So in fact, we were both working on this at the same time. This is the solution that Norfolk and Southern came up with. It said this is going to be the new rail line, and here I wish I had the one showing them both on two-dimensional, but here's the two different proposed track lines overlaid on top of each other. You can see they're quite similar for a major portion of it. The Norfolk and Southern line is actually a little less has less turns. Okay, see, there's less turns in the Norfolk and Southern line than there are in our proposed model route that took some turns. So perhaps what we could do is go back and evaluate our model, and perhaps what we could do is increase that total track cost, and that would prevent it from making so many turns, and it might get closer to what the Norfolk and Southern route, the traditional route chose. But regardless of that, it was very similar, and so it'd be helpful to know that was beforehand. It would have been helpful to know that this was a good route that could have been surveyed, and rather than looking at other potential routes that might have been expensive to survey. So this could help narrow down the possible path. All right. So that is the end of the lecture. Do you have any other questions about least cost path modeling, cost distance modeling? I did want to really quickly show that in ArcGIS. It takes a few seconds to download. You can download this or not. I don't believe this will be the same data that we'll use for the lab, but this is some data that I just downloaded of part of Forest and Lamar County, a LiDAR data set. And let me I'll just put it in C temp. Actually, I have that SA folder. I'll put it in there. SA. I'm just going to paste it in here. I called it files.gdb. It's not very good. Well, that was from last week. Let me open up a new one. I probably should close Windows every once in a while. Everybody always tells me that. Never know you when you're going to need it again, though. All right. I'm going to close this window up, and I'm going to add this data set. So C temp, oops, C SA and files.gdb. There are two files in there. I'm just going to load the DEM for now. Actually, I'll load that one for a second, and then I'll close it up because it's really a pain to load. So this is the LiDAR data set, the original LiDAR data set that the DEM was derived from. I downloaded this at what they call the Mississippi Geospatial Clearinghouse, and they have LiDAR data for a number of the counties that surround Camp Shelby. So this was acquired as part of a Camp Shelby project a few years back, and you can see these are all individual points. So the instrument collected these XYZ points of the ground, and I converted those into this DEM, which is something that we'll actually do later in the course, is convert from points to raster using interpolation. So there's a couple of different ways to do that. We'll talk about that. But this is the digital elevation model that I created. I should have loaded some other ancillary data so you could kind of get a feel for where you are. But you know, these are obviously rivers and streams. This is the Black Creek, and then these are rivers flowing into it. So Hattiesburg is like up here. This is kind of in the center of Forest Lamar County. Okay, so one thing that we should look at is if you look at this data here, you can see that it's in meters. Okay, meters. Now look at the elevation values. The elevation values range from 233 as the low to 420. Do those values seem like they're in meters? Now, what's the elevation around here? Somebody? Yeah, it's in that range. That 2 to I guess the highest in this area that's been cut out is 420 feet, which seems a little high, but maybe there's some big hill somewhere. And then yeah, the average elevation is somewhere in the high 200s.
How do you tell which unit the elevations?
The only way to really tell is to make sure that the people that gave you the data tell you. But we could look at this data for ourselves and tell that it's not in meters, because 200 meters is how many feet? Just approximately like 600 something feet. 400 meters is getting into 1,200 feet. I don't know if there's anywhere in Mississippi that's 1,200 feet. No. So there's a problem. But yeah, I looked, and it is in fact in feet. And so we'll talk about this a little bit more next week, but actually in the 2 or 3 weeks to come. But there's a problem if we kind of mix our units here. We've got meters in the X and Y. So X and Y would be this way, X, Y, those are meters. But we've got feet in the Z. And the first thing that I want to do is I want to calculate a cost that's just based on slope. In other words, I want to find a path between two locations in this data set, and I want my cost to be based on slope, meaning that I don't want to go up and down hills. I want to meander on the same contour if I can. And so in order to do that, the first step would be to convert the data set from digital elevation model in feet to a digital elevation model in meters to match the same units. Because if I calculate slope, okay, what is slope? We'll talk about that more next week, but you know, we know what slope is back from geometry. What's slope? It's rise over the run, right? Exactly. And so if we use the computer's method to calculate rise over run, it's going to calculate the run in meters and the rise in feet. So it's going to give us a slope value that's not correct. Now, it wouldn't really matter too much since it's just an example anyway. But our slope values would all seem low if we did that. So let's just convert this first from feet to meters. Anybody got a suggestion of how we could do that in map algebra? We've got DEM, right? And that needs to be converted from feet to meters. So what would you suggest? You don't have to come up with the exact number, but how would we convert feet to meters? What would be kind of an equation to do that? So assuming remember, the grid, the values in that DEM grid represent elevation in feet, and we want elevation in meters. Feet times 3. Okay. I think you're on the right track. You're doing good, but feet times 3, they're already in feet. So if we multiply them by 3, there's really 3 feet, almost 3 feet in a meter, right? And so it's kind of the opposite of what you're saying, because you're going, like, if we already had meters, we would multiply those by 3 to get feet. So we just need to do the opposite. Yeah, you could divide it by 5, or we can multiply it by, I just checked on the conversion factor here. It's we're going to multiply it by 0.3, which is the same thing as dividing by 3. But the exact factor is 0.3048. So that's the number to convert between, well, at least up to 4 decimal places, which is enough for what we're doing. So I'm going to put this in the same location, and I'm just going to call it DEM meters. Save it, and I'll run it. And we'll get a data set in meters. Maybe I should have done this beforehand. If this takes a long time, what we'll do? Nope. Yep. Sometimes computers, they tell you, make it sound like it's going to take forever. But okay, so now those numbers represent meters, much more reasonable numbers. Now we can calculate the slope, which we did in the last class a bit. We'll talk more about what's going on behind the scenes in the weeks to come, but we know how to calculate slope based on the last class. There is a tool for that under, why can't I find it? Surface, that's what it's under. So we'll calculate the slope and the slope of the DEM, and we'll have our output be degrees. Sometimes it's easier for us to think about degrees rather than the opposite. The other one's percent rise. Both of them work, but I'm going to call this DEM slope. Calculate it. You know, the Z factor is another way that we could have manipulated. We could have actually put the conversion factor right in there. Because it says the Z factor adjusts the units of measure for the Z units when they are different from the XY units. So we could put the conversion factor there, but I just did it as an earlier process. So now we have slope, and you can see here's the output of the slope map. Okay, let me zoom in here a little bit. Okay. So there aren't a whole lot of really high slopes, but there are some slopes. So this will be our only cost. The cost will be the slope in degrees. And so we want to come up with locations. All right. I didn't include a location to use, so one thing that we could do is we could create one. Okay, let's do that real quick. If you go into our catalog and you go to the location that you were in, we went to C, SA, and then files. If we create a new data set, new feature class, make it let's just call this source, and we're going to make it a point feature. And we're gonna make sure that it has the same projection. So I'm going to go in and say import, and I'm going to choose the DEM, and it's going to tell me, okay, it's in NAD 83 Mississippi UTM zone 16 north. I say okay, next. All this stuff I can just hit finish here. Okay, so now I've got this data set that represents the source, but I haven't specified where it is. I think I'll put it in one corner of the map. Like let's put it down here in the flat area somewhere. So in order to edit it, I don't know if you remember, we can go Where's the editor toolbar? So we turn on the editor toolbar. It's already on, I just can't see it. Where did it? I just turned it off. Did anybody see where it was? Okay, watch. Oh, there it is, right there, right in front of my face. So I could say start editing. And once I start editing, I can add a one guy right down. Let's see here. Open attribute table. This should be the edit tool. It's not choosing a point. Okay. Let's turn on the create features window. Sometimes you have to select on that guy. Yeah, there we go. Okay. I thought by default that was turned on. Okay, editor, stop editing. Save my edits. Now I'm going to calculate the least cost path distance. Sorry, not the least. I'm going to use cost distance. I'm going to calculate cost distance, and my source is going to be the data set I just created. The cost raster is going to be just my DEM slope, and then I'm not going to give it a maximum distance. I'm just going to say everything, and I'm going to call this cost distance based on slope, and I'm going to express this. Yeah, that's optional. Yeah, so this will be the backlink raster that we talked about. I'll just call this direction. Save. Okay. And let's see what this looks like when it's done. This does take a little bit longer. Hopefully, it doesn't take a whole long time. I should have clipped out a smaller region, the study area, so that each one would complete faster. But right now, it's using the slope as the cost factor. Lower slopes mean lower costs. So it's trying to find the distance from that source to the rest of the data set by considering the slope as the cost. The higher cost to travel through higher slope areas, basically. Let's see what the processing window says. Oh, it's not going to let me. All right, so the final step would be to find the least cost paths from some other destination or set of destinations when this completes. Just went a little bit faster. Machine was on. I'll give this like 2 minutes, and then we'll cancel out, and I'll make the slope grid smaller area. Might be able to just open this. See if this is producing a. Okay. Let's add the. I thought I put it right in CSA files. I don't see any of those other data sets. Where to put those guys? Okay. Hold on here. Okay. So I'm gonna get a smaller area here, and I'm gonna go and spatial analyst, slope, surface, slope, and watch. What I can do is do what I was going to say. Did I said earlier? Change this to 0.3048, and then change this value to. Let's see where I put these. Okay, SA. Nope. SA. Week 3. We'll call this DEM slope. And we've done this before in a lab. I've shown you this, but you can actually change the processing extent to be the same as display. So now, once I run this, the output is going to be just the display area. So it's going to run faster. So now if I run cost distance again on just that, well, I'll have to add the source in here. Oh, hopefully my source, yep, it's on there. Okay, so now I run cost distance, and I put the slope in as the cost, the source in as the source, and I'm going to call this cost P, and call this direction. Save. Run this. Still take. Let's close this one. Oh, yeah, let's close this one down so that the computer doesn't have to work so hard. All right, so we're calculating just the cost on this smaller area for it to calculate the cost distance. Still taking a lot longer than it did on my desktop. I don't know. I mean, I know it's an intensive process, but I'm surprised it's taking this long. Something wrong? Yeah. We could take a 5-minute break and come back, get a drink, and then we'll be able to see what it looks like. I think it'll finish in about 5 minutes. So I'll be right back. My hard drive filled up or something. See this. Okay. Nope. All right, well, we can pick this up at the lab time. I am going to leave it up here just because I'm curious, but y'all don't have to sit here and stare at it. I'll leave it up for another 10 minutes or so. But we can pick it up and talk about it in the lab, because that's what we're going to do this week. Is in the lab we're going to take create a cost surface that's going to be based on land cover. Oh, good finish. In the lab we're going to take a surface based on land cover and elevation and create a cost surface from just traveling from point A to point B. Okay. So this is the direction, okay? Whether you go from 1, 2, 3, 4, I said west, north, you know, in most maps, those are proper terms, but they're saying one is right, you know, east, and so on, okay? So if I turn this off, I have some other window that, okay. If I turn this off, I can see the cost distance. Okay. So in other words, if I wanted to figure out how to get from here, or not how much it's going to cost to get from here to here, then I have to click on that cell, and that cell will tell me the cost associated with traveling from there to there. And you can see that the cost is cheaper right here than it is, you know, in the surrounding areas. Also, there's this area. Let's look at the DEM and find out, and look at why that is. If we turn this off real quick, not the DEM, the slope grid, you can see that there's a pretty expensive thing right there. Okay, but so that's causing it to be more expensive to travel in that direction. But all this is pretty inexpensive. All this is relatively flat. Okay, and then the same with this peninsula up here. You can see this is all relatively flat, but this is kind of shielding air. This is expensive to travel through. This is a high slope area. This is a peninsula of low slope area, so low costs. See the costs associated with that. And so the final step here, if I wanted to, I could take my source data set and export this as a new feature. I'm going to save it in SA, whoops, CSA, and I'm going to call this destination. Okay, add it to the map. Editor, start editing. Let's see. So I'm going to put it right here, let's say. Okay. And then editor, stop editing, save edits. So I put my destination over there, and I could simply find out the cost path by putting in the destination data. And I don't need to put the source data in because everything is traveling to the source. And then I give it the cost distance raster and the direction raster, or the backlink raster is what ArcGIS calls it. And then I come up with my path here. And say path type, each cell, each zone. Okay, we don't have multiple paths. We only have one. We only have one destination, so we're only gonna have one path. So it doesn't really matter what we choose there. And so when this runs, which it ran, it's hard to see, but you could see that's the path that it's taking. And what I would suggest is to do a raster to vector conversion on that data set. So you could take that data set, go into data management, and say, let's take a raster or conversion. Nope, they moved conversion up to there. Okay, from raster to polyline, and give it the source. And I think we can just go okay. That'll make it so that we can symbolize it dark in a more dark fashion. So let's choose like a nice dark black. Okay, so now we can see that is the path that it chose, okay, through that area, and it chose a lower cost to get to that point. Okay. So, all right. Might be easiest to see on actually the original DEM. Let's look at that. Well, you know, it might look really cool on a hillshade, but we won't do that right now. So you can see how, well, maybe I'll make it, maybe I'll make it red. There we go. Now you can see how it traveled from this point to this point, and it went right up that river valley because the slopes are lowest on the river valley, and then went over. You know, when it had to, it made the connection here where it has to go over a watershed boundary, but it's a lower watershed boundary than, like, let's say if it hiked over that direction. So if you were, I don't know, making a walking path for a person that you didn't want them to have to go up large slopes, this would be a solution for that purpose. Okay? Trying to hike from point A to point B. Maybe you were going to go on a hike. But anyway, that's an example of least cost path modeling in practice, how you actually follow the steps through. So you can see the steps that we had to implement, and that'll take us to where we're going to go in the lab. We're actually going to drag those onto a canvas so that you can run them all at the same time. And ideally, where we want to go in the lab is allow the user to interactively change the weights. Say, okay, well, I want slope to be this much of a consideration. Well, I want land cover to be this much of a consideration. So we're going to make those parameters in our model. Okay, I don't want to walk through forests. I want to walk through open areas, or vice versa, or maybe so weighting those different costs in different ways. And
in this case, yeah, basically take forest and
right.
swampy. Yeah,
Yes,
it looks good in this case, but then we get there and see what the.
We could be up to our knees in mud,
Yeah.
right? And so there's other things to consider. Exactly. So if we don't want to walk in mud, we could make the cost to walk in mud very high, but we could still make slope another cost. So that's yeah, exactly. And then we would add those costs together, and it would choose a path then that was still as low slope as possible without going through mud, or maybe pass through mud just to the slope. If we were actually planning a walking trail, that might be an area that we could, if we had to travel through mud, it would minimize it, and that would be an area that maybe we could build a bridge or a boardwalk through it. Okay. Remember one of the first things I did when I moved to the south from out west was go to, they have this Congaree National Monument in the Nats National Park, I think, just outside of Columbia, South Carolina. And it was the middle of summer because we just moved out here going to graduate school. And so, hey, it's a national park, let's go. But it's a big swamp, lots of mosquitoes. And but there were boardwalks on the path. That's what made me think of that. Interesting. Okay, any other questions? So that's what we'll do for the lab. I didn't have a good reading this week, so you might want to go through and read as a suggestion, just read the cost path or the cost distance, the tools that we just used, or read the help for those, and see what you can glean from those before we execute our model in the lab this week. All right. Good. Well then, I'm pretty sure that it was able to save the lecture. See, it says whenever it says it's broadcasting, I'm pretty